Dear students, continuing with our fourth lecture on stereochemistry, today we will discuss about stereochemistry of enolates. Enolates, they are produced by deprotonation of aromatic alcohols, esters, aldehydes, and enolizable ketones. And this deprotonation is quantitative when we use strong base as the catalyst, and basically the protonation takes place because of the carbonyl function group, which is generally present, which makes the protons present at the alpha carbon very acidic in nature. The some of the common characteristics of these enolates, they are that they are usually produced when we use a strong base like lithium diisopropylamide, and these are produced in low concentrations with alkoxide bases if we use, which are not as strong as lithium diisopropylamide. And these alkoxide bases, they are used mainly in chelation condensations, managed reactions, and aldol condensations. But these enolates, even when they are present at low concentrations, they nevertheless they will always interact with the electrophiles, because nucleophiles will be produced, and these enolates, they will act as nucleophilic nature. Then this enolate behavior of these deprotonated compounds is dependent on variety of parameters, like counter cation, which is used. For example, as I told you, that lithium diisopropylamide is a strong base, so lithium cation, and in case of alkoxide bases, for example, sodium cation. Then the kind of counter cation which is present will also determine the type of enolate which is formed. Then the type of additives which are used for the formation of these enolates, like diamines, and the type of solvent which is being used for the production of these enolates. Then we can regulate the regiochemistry of the deprotonation of unsymmetrical ketones by controlling either counter cations or additives or solvents. Based on the type of additives or counter cations or solvent, we can change the regiochemistry of the enolate form. So we will take the example of aldol reaction, as we know that this is an important condensation reactions for formation of new carbon-carbon bonds in organic chemistry. And when carbonyl compounds like aldehydes or ketones, they condense with each other, and there will be a creation of up to two adjacent stereo centers by formation of a new carbon-carbon bond. And here one molecule of the carbonyl compound will act as a nucleophilic donor, whereas other carbonyl compound will act as electrophilic acceptor. And the aldol reaction, as you know, was discovered by P. Borodin in 1872, where he first observed the formation of aldol, that is 3-hydroxybutanol from acetaldehyde, when two molecules of acetaldehydes they were treated with catalysts such as hydrochloric acid or zinc chloride. Then this type of 3-hydroxybutanol was formed, which was called as aldol product. Now, when the aldol reaction mechanism was studied, it was found that the aldol product is formed through the formation of enolates, and the geometry of the enolate may be Z enolate or it may be E-enolate, depending upon the reaction conditions and nature of substituents which are present on the carbonyl compounds. For example, if we use strong bases like lithium diisopropylamide, which is a strong base, and the temperature of the reaction is low, at low temperature and shorter reaction time is used, this will lead to the formation of a kinetic enolate. Whereas when we use weak bases and the type of, for example, base is hydroxide ion or alkoxide ions, they are thought of as weak bases. We require high temperature and longer reaction times, and this will favor the formation of thermodynamic enolates. So basically what happens is when carbonyl compound is treated with the base, the acidic protons which are present at the alpha carbon, this is also alpha carbon, this is also alpha carbon. The proton will be extracted from the more acidic carbon which is present at the alpha position. So this proton will be abstracted from this carbon, and we will get this type of enolate formed, which is called as the kinetic enolate. Then this kinetic enolate is formed at low temperature and in the shorter reaction times. This kinetic enolate will then attack the second molecule of the carbonyl compound and abstract this proton, and this will be converted into this type of thermodynamic intermediate, and the carbonyl will be generated back. So this is how kinetic enolate can be converted into a thermodynamic enolate through transfer of energy. So as I've told you that in aldol reactions we have two condensation of two carbonyl compounds, and when we use two different carbonyl compounds, then all types of diastereomers they will be formed during the reaction, and how much of which type of diastereomer is formed will depend upon the type of enolate which is formed during the process, and this is determined by the reaction conditions and the nature of substituents present on the carbonyl compounds. So for example, if we are having this one carbonyl compound which reacts with, this is a ketone, this reacts with an aldehyde, then we will get this type of syn product and anti-product formed. So four type of diastereomeric products they will be formed. Now, when the reaction proceeds through thermodynamic control, that is when we are using a weak base for a high temperature and longer reaction times, then Z and E forms of the enolates, they are in rapid equilibrium, and the amount of syn or anti-product, that is the different diastereomers which can be formed, depends by the relative stability of the six-membered chair-shaped cyclic transition state which is involved during the formation of Z-enolate and E-enolate. So for example, when in the first step the carbonyl compounds undergo deprotonation, it will be converted into Z-enolate or E-enolate. and then this Z-enolate or E-enolate will react with the other carbonyl compound. Say this is ketone, this is aldehyde. Then two types of transition states they are formed from this process. So in one process, at this transition state is a six-membered chair-shaped cyclic transition state. So the transition state will lead to a syn product where the R1 substituent, which is present in the axial position, whereas anti-product is formed where this R1 will be in the equatorial position. So the major product formed will be anti-product because this equatorial state is more stable in comparison to axial state of the this substituent. Similarly, if the reaction take place through kinetic control, that is when we are using strong bases, low temperature and smaller reaction time. So for example, you can say see that the reaction is proceeded with strong base and at low temperature, that is minus 78 degrees centigrade. Example is in case of 2,2-dimethyl pentane 3-one or 2-methyl pentane 3-one, you can see the only difference is the steric hindrance present due to this bigger group in comparison to a smaller isopropyl group. So when in this case, in case of 2,2-dimethyl pentane 3-one, the Z-enolate is normally favored over the E-enolate, and the product formed is a syn product with 91% of enantiomeric excess or diastereomeric excess. Whereas when we use 2-methyl pentane 3-one, when this alkyl group is reduced from this tertiary butyl to isopropyl, this is a smaller group in comparison to tertiary butyl group. So because of this, the ratio of the product formation from Z to E is 4:1. So if 20% of this is formed, then 80% of syn product is formed. So this all other conditions they are same, base is same, temperature is same, reaction time is same. So the steric nature of the substituent present determines that how much diastereoselectivity will be there in the product formation. The geometry of these enolates has been thoroughly studied, and mechanism suggests that when we use ketones, the preferred enolate is the Z-enolate. But if instead of ketones we use esters, then most of the enolization conditions they will give us the E-enolate. For example, if we are having say this ester, this when we use a strong base at low temperature for a smaller reaction time, this is the favorable transition state where there is a low interaction between these two axial group. This hydrogen is a smaller group and there will be this isopropyl group is a bigger group, so the interaction between these groups is low, and because of that this transition state is more stable in comparison to this transition state where the isopropyl group present on the base has more interaction with the bigger methyl group. Here methyl group is axial, whereas here methyl group is equatorial. So when bigger group is in equatorial position, that transition state is more stabilized, and this will lead to the formation of E-enolate, which will lead to the formation of the product. Similarly, if in addition to the base we use 23% HMPA, that is hexamethylphosphoramide, then they will form such a complex that the unfavorable transition state product is formed, that is Z-enolate is formed in more amount, as the major product formation will be done through Z-enolates. The stereoselective formation of these enolates has been rationalized through Ireland model. Although in many examples Ireland model is not able to explain the formation of products, but still this is the more accurate model for deprotonation of different types of ketones, which says that six-membered cyclic monomeric transition state is involved in the formation of enolates. And as I have told you, that larger of the two substituents present over here, that should be in the equatorial position, and that enolate formed will be the major product. So in case of esters, E-enolates, they are preferred over Z-enolates because of the unfavorable transition state, because bigger group is in the axial position, and that will interact with the bigger group present on the strong base. Then some examples, for example, if we see that we conduct the aldol reaction of this ketone, and in this case the effect of the base which is used will determine that which type of enolate will be formed. For example, if we are using boron compounds, dibutyl boron triplet, which is formed from this dibutyl boron with triplet trifluorosulfonyl chloride on reaction with boron, trifluorosulfonic acid reacts with dibutyl boron to give you this base. This in the presence of diisopropyl ethylamine, they will give us Z-enolates as the major intermediates, which will react with aldehyde to give us a syn product in 99% amount. Similarly, if we change this base from dicyclohexyl boron chloride from dibutyl boron triplet under the similar conditions, then E-enolate is preferred because of the nature of the electrophile which is attached to the oxygen over here in the formation of enolate, and this will lead to an anti-product in more than 97% amount. So we can see that the type of the base used can also affect the formation of different types of enolates, or we can say the stereochemistry of the enolate is affected by the type of the base which we use for deprotonation of the ketones. So these are the references which have been used for preparing this lecture. Thank you very much.